Hello, my name is Steve Pescatelli. I'm a streams biologist with the Illinois Department of Natural Resources Division of Fisheries. And I'm here today to talk to you about dams and their impacts on stream ecosystems. It's well known that dams have a significant negative impact on stream ecosystems throughout the country, and in fact they've been implicated as one of the primary sources of the loss of mussel and fish diversity throughout the country. For that reason, there's been a big movement to remove dams, particularly those that don't serve any purpose anymore. They're old and obsolete. And about 1,600 or over 1,600 dams have been removed nationwide. So that produced a lot of restoration, a lot of free-flowing miles of stream. Over the last 25 years, I've been working on this issue in northeastern Illinois, and we've made some significant progress over the last few years. And in fact, we've completed 35 dam projects in northeastern Illinois and seen tremendous benefits in stream restoration from these removals. It's rare that in your career you come across a solution to the problem, a problem that is so immediate and measurable, and that's what dam removal does to a stream ecosystem. So we've had the opportunity to study these dam removals and to document the benefit from the stream restoration that results from the dam removal. And we see an incredible restoration of the areas upstream in the former dam pools, an increase in number of fish, the number of fish species, and the stream quality. And what's more exciting is we see fish move back into areas where they haven't been for a long time because of the dam. Dams historically and pretty reliably reduce the diversity in the upstream areas. This is particularly important in areas that have suffered historic water quality problems, like Salt Creek, for example, where a lot of the native species have been extirpated. So we remove the dam and the fish respond and swim upstream, and we see an increase in quality in the upstream areas all the way up the watershed until they reach the next dam in some cases. So, like I said, dam removal is the most cost-effective way to improve a stream and to restore a stream. And it's kind of a return on our investment of all the money we've spent on improving water quality over the years, so these fish can get back into their native areas and take advantage of all the progress we've made in improving water quality.
My name is Alan Lang, Director of Public Works for the City of Wooddale. The city is pleased to participate in improving the fish population and water quality in Salt Creek. Dam modification is the most cost-effective measure to achieve this goal and doesn't place undue burden on taxpayers to cover the cost of increased wastewater treatment expenses in the future.
My name is Rick Federighi. I'm the Director of Public Works for the Village of Addison. Stream improvements, like the recently completed one here at the beautiful preserve at Oak Meadows in Addison along Salt Creek, are very effective ways to improve water quality. It's a treasure that we have here in Addison, and it's a type of projects that those in my industry that operate wastewater treatment plants that are concerned about water quality, we encourage and support these types of developments. Whether it's through the stabilization of stream banks, stream restorations and re-meandering of the streams, or most importantly, the removal of dams. These are all great strategies to help improve water quality and serve as an alternative to expensive upgrades in treatment technologies, installation of equipment, and the use of chemicals at our wastewater plants throughout DuPage County. We feel this is a win-win for the citizens of DuPage County, where these types of environmental improvements can be made while at the same time saving taxpayer dollars.
Why would anyone want to remove the dam at Fullersburg Woods, Salt Creek? The aim of this presentation is to outline the reasoning behind the proposal to modify the dam. The project under consideration is an essential piece of restoring the ecology of Salt Creek Basin. To fully understand the push to do this, one needs to start with the 1972 Clean Water Act. It set out to achieve the broad goal of restoring and maintaining the chemical, physical, and biological integrity of the nation's waters so that they can support the protection and propagation of fish, shellfish, and wildlife and recreation in and on the water. The Clean Water Act made it unlawful to discharge any pollutant from a point source into navigable waters without a permit. EPA's National Pollutant Discharge Elimination System, or NPDES, permit program controls these point source discharges. All sewage treatment plants discharging to Salt Creek and its tributaries have such a permit. It is estimated that over $1 trillion have been spent in developing wastewater infrastructure since 1972. These permits are reviewed on 5-year intervals and are changed based on the results of an evaluation published by the state called the State Integrated Report and 303D list. This slide shows a summary for the segment of which Growy Mill Dam lies, pulled from the 2018 report. The river segment fails to meet the Clean Water Act goals in a number of regards, as we can see in the highlighted box. We will be focusing on aquatic life because it is the most common driver in area wastewater treatment plant permits. Others, for example, such as fish consumption, tend to be due to legacy pollutants that have already been banned nationally. We have highlighted the areas relevant to the dam in red text, and you can see it referenced in several areas. The state does not, however, move on such causes in a regulatory action, as they do not currently have the means to force entities to act on such items as dam removal or habitat improvement. That is, it can be demonstrated that a structure such as a dam is the cause of not reaching a goal, but the state cannot compel anyone to fix it. Rather, regulatory action tends to fall on wastewater treatment plants, as the process for doing so is understood and well developed. Causes associated with wastewater treatment plants are referenced here in blue, and they include such items as phosphorus and dissolved oxygen. Again, the table does reference removal or the presence of the dam in several areas. As we saw, the state has shown that the waterway is not supporting aquatic life to the Clean Water Act threshold. The state also noted that the river had low levels of dissolved oxygen and suggested that as a potential cause of the missing aquatic life. In 2004, the state produced a total maximum daily load, or TMDL, type of water pollutant budget for the Lower Salt Creek, and recommended decreasing in the permitted amounts of certain pollutant parameters. This was done despite the fact that all the plants were already discharging these pollutants beneath the state's water quality standards. The state ran a number of scenarios, which included stricter limits at wastewater treatment plants and the removal of the Growy Mill Dam. This can be seen on the left of the image. These scenarios were to set out a pathway to gaining water quality compliance. There was, however, a flaw in the analysis. The model assumed that wastewater treatment plants were using the whole of their permit allocation when explaining the observed water quality in the river. In fact, they were only using a percentage of their allocation, meaning that the model both blamed them for more of the observed problem than they were actually responsible for, and also assumed that they could do more to fix it than they actually could. Their actual treatment levels were actually very close to those recommended by the TMDL. Wastewater treatment plants only use a portion of their permit allocation in order to maintain a margin of safety in the face of unpredictable factors such as weather that can affect treatment levels. Treating at permit levels would mean constant violations of the permit. Operating at 60–70% of the permit allocation avoids this. IEPA did acknowledge this problem with the model and consented to a re-examination of the dissolved oxygen situation in Salt Creek. If wastewater treatment plants were already operating near the levels suggested in the TMDL, what was causing the low dissolved oxygen problem in Salt Creek? Costs of implementing the TMDL, as set out in the scenarios on the left of your screen, were estimated at $213 million in capital upgrades at wastewater treatment plants in 2020 dollars. This would largely be done to maintain their margin of safety. This slide shows the updated model for Salt Creek developed by the DRSCW. The black line running through the middle of the graph shows average daily dissolved oxygen, and the red dashed line beneath it shows the daily minimum dissolved oxygen. DO moves around in a 24-hour cycle, hence these two lines. The three vertical gray lines represent dams on Salt Creek, with Growy Mill Dam being the one on the right of your screen. This output from the model represents hot, dry weather conditions, classic for low dissolved oxygen. As you can see, the major drop predicted in dissolved oxygen is behind the Growy Mill Dam. This model was built using hourly observed dissolved oxygen, actual wastewater treatment plant discharges, and even actual measures of how much oxygen was being consumed by the sediment, a major issue in our waterways. All these inputs made it a more accurate and more data-intensive effort than the original model developed by the state. The model was used to simulate setting all oxygen-demanding pollutants coming from wastewater treatment plants to zero, a technically implausible proposition. Even at this level of treatment, the model did not predict elimination of the dissolved oxygen problem upstream of the Growy Mill Dam. The state reviewed the model and its findings and agreed with its conclusions. It negotiated with the DRSCW to postpone the implementation of its TMDL if the two dams at Oak Meadows and the Growy Mill were removed. Dissolved oxygen itself is really a proxy for aquatic life, which is measured by insect and fish populations. The state's interest in dissolved oxygen is because it is an important water chemistry indicator of the river's ability to support aquatic life. However, it is not the only one. The DRSCW also looked at a number of factors, including intensively mapping out the aquatic populations, fish and insects, that the state used to measure Clean Water Act compliance. The following data is not from a model like the previous slide. They are actual observed data collected over a number of years using the state methodology for sampling and scoring. This graph of fish biodiversity on Salt Creek was gathered using the state system. The light gray box in the center of the graph marks the target area for compliance, with its upper boundary showing compliance with the state standard. As you can see, the species fall after passing the dam, marked here by a red arrow, and do not recover. Fish found further upstream receive a higher score under this state system, so each of the 16 target species currently constrained by the dam would increase their scores as they move further and further upstream. Also note that after the fall at the dam, the population or species biodiversity does not recover as we move upstream outside the area of flow impacted by the dam. There is no doubt that removal of the dam will allow these fish to move upstream, bringing huge environmental improvements and regulatory relief to local governments. Here are the fish species limited by the dam. The column to the left of your screen is the list of fish trapped downstream of the dam. 18 fish are listed here, 16 of them are native. The second column shows fish that are limited on the upstream side of the dam, 2 species. On the images, the image at the bottom right of your screen shows a northern pike that was caught just south of the dam. This pike measured 32 inches. Surveys show that such species are common beneath the dam. The second image shows a long-nosed gar. This is not an image of the actual fish that we captured in 2016, but it was a cause for some celebration, as this species had not previously been found on Salt Creek during any of our surveys. It appears to be the product of the removal of the Hoffman Dam on the Des Plaines River in 2012. This graph shows the aquatic insect population on Salt Creek. This is the second one of the aquatic populations needed to meet compliance with the Clean Water Act aquatic life goal. The yellow box in the center of the graph marks the target area with its upper boundary showing compliance. Again, Growy Mill Dam is shown by the red arrow. The large drop in aquatic insects associated with the dam is clear. This is due to the massive negative habitat impacts created by the dam, largely the impact of sediment buildup behind the dam. The sediment deposited in the impoundment blankets, gravel substrates, and riffles, making them uninhabitable. Such habitat can be restored by removing a dam, and where this has been done, recovery of the insect population has been highly successful. Note that unlike the fish population, we do see recovery of the insect population once we move outside the area of influence of the dam. This is because insects, unlike fish, can fly to new locations to set up new populations. This slide shows the habitat along the Salt Creek. Again, the dam is shown by a red arrow. And again, clearly associated with the dam is some of the worst habitat conditions on the creek, despite the fact that the dam itself is in a forest preserve. You may note that the habitat graph looks very similar to the preceding insect graph. And it's true that the two track very closely. Habitat itself does not typically appear in MPDS permits, but it is impossible to reach the Clean Water Act goals without having sufficient high-quality aquatic habitat. What are the options to solve these problems? The column on the left, outlined in yellow, shows some of the options that we've examined to do this. These include removal of the dam, upgrading of wastewater treatment plants, aerating the dam impoundment, dredging, and placement of a fish ladder. The cost for these alternatives is given in column 2, highlighted in orange. The remaining columns show how the intervention resolves the issues faced by regulated entities: improvement of dissolved oxygen, establishing fish passage, establishing insect populations, and improving habitat. Dam removal is the only one that tackles all of these. It does so in a cost-effective and highly predictable manner, and at the cost of approximately $4.2 million for removal of the dam, rebuilding of the stream corridor, and work to maintain flow in the Growie Mill Raceway, this is much more cost effective than upgrading treatment plants, which, while that may improve dissolved oxygen, cannot fix fish passage, improve habitat, or the insect populations. And it will cost approximately $213 million. Based on the magnitude of the cost savings for tax and utility bill payers, the high level of confidence in getting the desired results, and the range of improvements that it can deliver, the DRCW is recommending removal of the dam at Fullersburg Woods. Lastly, it should be noted that change is underway at the dam, whether the DRSCW project moves forward or not. This is an aerial image of the Fullersburg Woods Dam shot in 2018 during a water drawdown. The view here, taken from a drone, is looking south towards the dam, and the mill building can be seen in the middle of the image slightly to the left. Here, the sediment beds that are building up are clearly visible on the east of the channel and again around the mill raceway intake. This sediment will continue to accumulate, and the impoundment will increasingly come to resemble a sluggish stream. Indeed, these sediment beds are already visible even during normal water flows. Dredging of such beds is very expensive even when the sediment is classified as clean. Such dredging is fraught with permitting issues. Removal of the dam will allow this sediment to be managed as part of the dam project. This image is taken from a similar position looking south towards the dam, but taken at the surface of the water. This is without water drawdown taking place and allows image of the poor water quality that we encounter behind dams to be clearly seen.